All right, so today I'm going to talk about some of the new work we're doing on improving computational efficient power descent guidance via transformer-based tight constraint prediction. But before I get into that, I really want to give an overview of the work that I do in my group and some of the AI-related work that we're doing in space. So this is my group at MIT, ARC Lab. So we're the Astronautics, Space Robotics, and Controls Lab, and we focus on these 4 areas. Today you'll hear a lot about the work we're doing in AI for space, but I do want to mention some of the other work we're doing in my group. We do a lot of work in space sustainability and understanding space debris and how that's going to be an ever-increasing problem for the space population. You saw that. Obviously, everyone in the world saw the solar storm that happened a few weeks ago. So we do a lot of work in space weather. So that was a really big storm. But even the minor storms has effect on satellites. And so we do a lot of work there. Analytical astrodynamics. So like Marco mentioned earlier, space dynamics. So we do a lot of work in space dynamics, understanding trajectories of satellites and how to improve modeling of those trajectories. But what I want to talk to you about today is a lot of the work we're doing in entry, descent, and landing, and in particular, the guidance problem there. So optimal control approaches to power descent guidance are not computationally efficient enough for the types of things that we want to do in space. And so the issue is that we have resource-constrained processors, and we might need to solve these optimal control problems over long horizons. So how are things currently done in space? So this sort of equation here is not too far from where the state of practice is. So this equation is very similar to something that folks in the room that have done space have heard of, which is called the Apollo guidance solution. So during Apollo, we had these polynomial guidance solutions. Now, these guidance solutions are very simplified optimal control problems. Typically, you consider it a flat planet, flat planetary body, so gravity pointing along the z direction, and energy-based cost function. Under those assumptions, and with no constraints, you can derive a polynomial-based guidance solution, and then you can do things like fitting the coefficients of that polynomial-based guidance solution to actually deliver a practical implementation. So that's something that NASA and JPL and ESA are using for some of their entry descent guidance applications. Of course, one of the most sort of impactful work done in this area is SpaceX and the reusable launch capability with Falcon 9. And they've done short horizon optimal maneuvers. So a lot of that work is using successive convexification and lossless convexification of the entry descent landing problem. But they're really looking at short horizon near the power descent initiation and calculating optimal maneuvers. So it's a step forward. But in reality, we're looking to deliver humans and exploration missions to other planets. And we have really high mass requirements for going to Mars and returning to the moon, because there might be humans on board. And the high mass requirements really pushes the envelope in terms of what we can do. So we're going to need fuel-optimal solutions. And we might need to execute large diverts. So we might be landing in more interesting locations where we don't have good maps. So the accuracy of the maps of the areas that we're landing might require large diverts. So now what I'm going to do is I'm going to do a quick overview of a lot of the work that we're doing in this area before getting to the main topic of the talk. So what have we done in this area? What are some interesting things that we've looked at? So in the past, we've done a lot of deep reinforcement learning approaches to try to alleviate this problem of real-time closed-loop guidance solutions for the entry, descent, and landing problem. So one of the issues that we have in entry, descent, and landing is how do we move from simplified 3 degree of freedom solutions, so you think about this as a point mass particle, to 6 degree of freedom solutions that have complicated actuator geometry and take into account the rotation of the craft. So that's very difficult to do, and that's one problem where like a reinforcement learning, a neural network-based solution, we've been able to show in the literature can help us solve that problem. So for example, here we have a fairly large divert area, and what I'm showing here is sampling of the train trajectory. And over this large divert area, we can use a reinforcement learning solution to learn not necessarily optimal trajectory. This is using a technique called GPOPs to optimize the trajectory with our neural network solution. So we can learn how to do closed loop guidance. We pay a penalty in terms of optimality. Optimality here is paid in terms of either time to landing or fuel mass use. So you pay a penalty in optimality, but you do get a closed form or a closed loop 6 degree of freedom solution. Other things we've looked at it with reinforcement learning is what about when we have things that we can't model very accurately on board, or we have changing environments? So one problem that's really interesting is landing a craft on an asteroid or a small body. So in this case, the rotational state of the small body might be something you measure. The actual map of the landing location might be uncertain. And so you're taking in these measurements, and what you have to do is, in closed loop, decide what trajectory the craft is going to follow to land safely on the body. And this is a really nice application for meta reinforcement learning. And the reason for that is we can deal with things such as unknown dynamics for the asteroid if the gravitational field is not fully resolved, landing under a non-Markov observation process, we don't have the full state information, or dealing with cases like engine failure, large mass variations. And for the folks that are not familiar with meta-RL, it's a really nice approach because it allows you to adapt online to any of these situations. So if one of your engine fails, you can adapt and handle that. Other things that we've been doing in terms of learning-based approaches for this problem is, those polynomial solutions that NASA and ESA use, they like them because they're very simple, and you can do things like analytically calculate provable stability bounds. But obviously, they're not fuel optimal, and they're relatively simple. What if we can do things like adaptive guidance, where we treat the coefficients as adaptive terms that are learned through simulation and can adapt online? So here what we're showing you is an adaptive guidance solution where, sorry, it's hard to see here on the screen, but the red curve here is the classical solution, the black curve is the optimal solution, and the blue curve is the adaptive solution. You see the classical solution can't deal with this keep out zone constraint where we have a landing zone that is in this valley, and so the glide slope here can be pretty steep. And so the classical solution, if you're coming in with too much velocity, can't handle this constraint here. Whereas the numerical solution can obviously really easily handle that constraint, but it's computationally expensive. With some of these reinforcement learning solutions, we can have the same structure as the classical solution, have the same provable guarantees, but be able to handle more complicated scenarios. And then finally, many of you that have done work in this area, you know that terrain relative navigation is a big problem. That's something that we're really interested for landing on the moon, landing on Mars. We might not have GPS on these planets. We definitely don't have it now, but in the future, the moon might have GPS. And in this case, what we want to do is, can we take this terrain information, use it to derive a optimal control policy? And so the way we do this is, in simulation, we train a reinforcement learning agent to analyze this terrain information and determine where is a safe landing location and decide on where it should land. So the way this will work is you have sub-policies, and you might have a hovering policy that hovers over a given location, looking for a safe location to land. And then once that safe location to land has been identified, the policy might switch, and then you enter into the terminal descent policy and land on a given location. And so things like this are really the types of problems that we're trying to solve in this area, just to kind of give you guys a motivation and a feel for the breadth of problems in power descent guidance. Now I'm going to talk about the main topic of this talk, which is the power descent guidance that we've been doing using transformers to predict tight constraints. So we have a paper that we've presented at the SciTech conference. If anyone's interested in the code for this work, here's our GitHub link. And I just want to acknowledge the main student that's been really great at pushing this work forward. Fantastic, Julia Brighton. And this is the work that she's been working on. All right, so what's the motivation for this? Well, for rover applications, we might have a simplified approach for helping us deal with constraints. So consider this rover going from this location to the green dot, and we have this complicated constraint geometry. These are keep-out zone. These might be craters. And we might know where these keep-out zones are ahead of time, but we want to online plan a path from the starting location to this goal. So one technique to do that are these search-based planners. So the search-based planners can find a solution for this problem under relatively low fidelity dynamics and without potentially actuator constraints. Then we take that solution and we might pass that solution into a model predictive control scheme. And then the model predictive control scheme, this is a movie. Sorry, I must have clicked through it. All right, well, anyways, it's a movie. The model predictive control scheme takes this solution here and further refines that for more complex actuator dynamics and control schemes. So this sort of structure, having some initial guess, some information about the structure of the problem, then passing that to a model predictive control scheme, this is something that's commonly done and is appealing. And then so our motivating goal is, can we do something like that for entry, descent, landing guidance? And let's talk about that problem in particular. And so the solution we're proposing is we've done a lot of work here on model-free RL. And then model-free RL, you can do things like closed-loop guidance. It's fast. And then on the other side of the spectrum, you have sequential quadratic programming, which is the alternative approach, which is formulate the optimal control problem, either convexify or convert that optimal control problem into a sequence of quadratic problems that you then solve, which can be computationally expensive and might not be real time for space applications. And then somewhere in between is the approach that we're shooting for. We're not necessarily model-free, so we don't want to necessarily be model-free, but we want to speed up this quadratic programming problem for the entry, descent, landing problem. All right, so let's talk about how we can improve the computational efficiency of the powered descent problem. All right, so to accomplish precise landing, the goal you want to think about is we want to have computational trajectories on the order of milliseconds. So for other applications, doesn't sound too bad, but you have to remember in space we have very constrained hardware. So our space hardware that are on these rovers, hardware that are on these entry, descent, landing vehicles are constrained. And so the trajectory generation problem for space, as many of you have seen in this robotics seminar in class, is we can define that by defining a cost function and defining a set of constraints. So there's equations of motion that become our constraints, and there's additional control constraints that we have. And then that problem looks something like this. So for example, we might have a terminal cost term, a running cost term, our equations of motion, some inequality constraints that we have to deal with, and then some boundary conditions. And this is really a general formulation of the problem. In a second, I'll show you what it looks like specifically for the space problem. So the equations of motion, those are equality constraints. Inequality constraints might be, Inequality constraints might be dynamic constraints on the vehicle, glide slope constraints, fuel constraints. And the boundary conditions might be if you have a fixed final time or if you start at an initial position. OK, so then the typical scheme here is then to map this non-convex formulation into a second-order cone program through a process of lossless convexification. And so this is a very common technique in powered descent landing in the last few years. This technique is similar to the technique that SpaceX uses for Falcon 9. It was developed by Bicek and, sorry, I'm drawing a blank on the second author's name, Larmor at SpaceX in the early 2015 timeframe. And essentially, this can convert this into a second-order cone program that we can solve using a convex solver. But the issue here is that we have to assume a fixed final time. The other issue here is after we go through the discretization of this problem, so I'll just mention before I go to the next step. So just looking back at this problem, so what's specific about this powered descent landing problem that we have is the dynamic equations is given by these two equations, but we are also adding a mass dynamics equation. So the thrusting, turning on the entry, descent, landing is going to change the mass of the craft, which changes our dynamics. Then we have these complicated constraints. So some of these constraints have to do with the thrust-to-weight ratio of the craft, maximum lower bounds, the control vector constraints. We can't point the thrust in any given direction. Tilt constraints, so the craft can't tilt horizontally. Glide slope constraint, we can't come in at too much of an aggressive angle. Dry mass, so there's actual structural mass that we have in the vehicle, and fuel rate constraints. There's only so much fuel rate that we can put through the engine, so we have that as a constraint. And then finally here we have our equality constraints, initial conditions, final conditions. The thing to point out about all of these constraints is these constraints here are always active. We always have to follow the dynamics. These constraints down here are always active as well, the initial condition constraints and the active constraints. These constraints here are complex and make the problem harder to solve, but are not necessarily always active. Okay, so we can convert this continuous time problem into a discrete time problem by discretizing our trajectory and considering n nodes. So this is your sort of classical direct optimization method, and we can solve this with an interior point method or an alternative solver. But essentially, we convert these continuous equations here to sets of discrete constraints. So we might have n control points. So if we have n control points, the total number of constraints are 15n plus 9. The 15n are these constraints here that are a function of n, number of control points. So we're discretizing the trajectory. At each point of the trajectory, our dynamics must be valid. And then these equality or inequality constraints must be valid at each point of the trajectory. And then at these 2 points of the trajectory, our boundary conditions constraints must be valid. So 15n plus 9. And then if we look at this problem, this is the crux of the problem and our ability to solve this in real time. So if we look at this 15n plus 9, these are the total number of constraints. As we start increasing the size of the problem from a smallish problem, you can think about those smaller problems as solving a rover on a lunar surface under simplified dynamics, all the way to the problem that I showed you on the last slide with complex dynamics. As you start increasing the size of the problem, which you might need more control points for, the number of constraints grows. It grows linearly, but it can get quite large for running on board. But if you look at the difference between the constraints that we're always going to have, which is this green line here, and then the constraints that might be active or inactive, there's actually quite a big difference in the size of problem that you're solving. So if ahead of time, if you had an indication on which constraints are active, you can reduce the size of the problem significantly and maybe alleviate some of the runtime issues that we're having for onboard computation. So here's the idea of the tight constraint prediction. So we want to be able to predict two things. I said last on the previous chart that for entry, descent, landing, powered descent, the final time in those equations, if we fix the final time, we can convert that into a coning problem with fixed final time. But if we want to solve problems with free final time, then we can give an estimate of the final time to that problem and still use the setup there. The other thing we can do is we can try to estimate which constraints are tight. So what we want to do is we want to learn a mapping between parameters. So these parameters are relevant dynamical parameters of the vehicle and a strategy. The strategy might be, which tight constraints do I go for? What optimal final time should I shoot for? And we can leave that final time fixed or iterate on that final time to increase the fuel optimality. And so essentially what we do is we input states that look like this: initial velocity, position, glide slope, pointing angle, engine angle, and then we output a representation that looks like this. And so this is outputted essentially as a one-hot vector, and identifying which one of these constraints are active for that particular problem and a fixed final time. Then we go back with this information, and we solve this problem here. And we've basically looked at which one of these constraints are active and removed the ones that are inactive, and now we're solving that problem. All right, so the goal here is to learn a mapping between the problem parameters and the optimal strategy. And so optimal, you might not use transformers. That's the approach that we chose. But you could use optimal classification trees. You could use feed-forward neural networks. But we've tried those things. They've been shown to be less accurate. And then unlike transformer and LSTMs, what we've seen in our work is that transformer-based neural networks process the entire sequence in parallel and can attend over the entire input sequence and derive what the relationships are between the elements to give us which constraints are more likely to be active. And so this is what the setup looks like. So we have an input vector here. These are our parameters that are the input to the transformer. They're a state representation of the problem given before. And the idea is that the transformer is going to output which constraints are active and the final time. And now with the quadratic programming problem I showed on the last slide, we can use this initial guess, this initial constraint activation to solve the problem in a lot faster, in a lot shorter amount of time. So this is the process for training the problem setup that we have. So we choose, this is during training data, we choose a bunch of initial state vectors, and we solve this problem repeatedly during training. We give that to our second-order coding problem solver, and then that problem outputs which constraints are active for the optimal solution, which constraints are active, and the optimal final time. Then we build a data set of, for certain initial states, which constraints are active and what the final time is, and then we train this transformer in PyTorch in this case, and then we test the network. And then in real-time applications, this is what it looks like on board of a spacecraft. So you might have your initial state, which is determined from sensors. That initial state goes into the neural network transformer architecture, and it outputs which constraints are going to be tight for that particular problem and an estimate of the final time. Then that goes to a fixed final time solver that for a fixed final time, that optimal estimate, and the active constraints determines whether things are feasible and also outputs the trajectory. If things are not feasible during that case, then you feed that back in, and then you adjust the final time by making it longer, making the final time longer until you find a feasible trajectory. So this is what some of the solutions look like. So in this case, we did 50 discrete nodes, and we generated, for training data, 242,000 samples. 80% were training, 20% were testing, and we benchmarked the transformer for this application, and it was the benchmark without the transformer for this application was about 1,600 milliseconds plus or minus 300. So that's without the transformer. So that can't run on board for that particular problem I showed you, fixed final time. That's not going to be able to run on board. So with the transformer-based method, we were able to reduce the computational time by 78%, just by predicting which constraints are active and getting a better estimate of the final time. And now the runtime, the mean runtime was 373 milliseconds with a standard deviation of 600 milliseconds. Now that's, you can consider that maybe a little bit borderline, but that's within the realm of things that we can run on board. And in this case, 100% of the trajectories were feasible. Now, if you don't find any feasible trajectories, then you sort of iterate your quadratic program solver until you get a feasible trajectory. But in this case in our test data, we had 100% of the trajectories were feasible. But that's not to say that in some cases you might generate non-feasible trajectories. So I do want to talk a little bit briefly about how to interpret this, how to understand this. And so one way to understand this is that what the transformer is trying to do through learning the embedding is learning these sections of the state space that might behave differently. So you can think about these sections of the state space as being these linear planes in a high-dimensional space that behave differently when it comes to solving the optimal solution. And these different sections might have different constraints that are active. So you might be able to group these into different clusters that have different constraints that are active and might have different final times. So the idea is the transformer is learning some sort of pattern like this. Can we look at a similar technique like a T-SNEAL to try to identify what are the patterns that the transformer is learning? So what we did here is we used T-SNEAL with the transformer. So we took initial input data for the transformer. When does it predict that constraints are active for the data? When does it predict that the less constraints are active? So in this case, you have the number of constraints that are active here. And we saw that there was this clear grouping of two structures in the transformer's learned behavior. There's this cluster here where a lot of active constraints were active. And there's this cluster here where not many of the constraints were active. And so we have more tight constraints with this cluster, less tight constraints with that cluster. So there was two clear clusters in analyzing the data. But when we looked at interpreting this data and looked at the performance, we also saw another pattern. This cluster here, cluster 2, which on the last slide is where less constraints were active, had a much tighter final position bound. So these were easier problems. And somehow the transformer was able to identify these easier problems. And you can see that their landing position accuracy was much tighter. Their landing velocity, the z velocity, was much tighter here. And the initial z position and glide slope angle here was much tighter for those problems. And then for cluster 2, these are the hard problems. These are the problems where there are a lot of constraints that are active. And in these cases, it might take longer for you to find a solution because there's more constraints that are active. But these are the problems that might have wide diverts. So the initial position deviation can be fairly large. The glide slope angle deviation can be fairly large. So really, you see this pattern here that there's sort of two classes of initial conditions: the hard problems with a lot of tight constraints and the problems that have very few tight constraints. And if we look at the variation, the standard variation of the position for these two problems, you can see that these hard problems, much larger standard deviation, higher velocities, and higher initial positions. All right, so in conclusion, by leveraging the intention mechanism of the transformer-based powered descent guidance enables millisecond-level prediction of the optimal strategy, which reduces the runtime of 3 degrees of freedom landing. I showed you 6 degrees of freedom when I did a survey of all of the work that we've done. That's really where we want to go with this work. 3 degrees of freedom is great, and you can implement that. And one way to really solve this for on board is you basically separate the problems. The attitude problem and the position problem become two separate problems. You solve the 3 degrees of freedom problem this way, and then you close the loop for an attitude controller. That might not necessarily be optimal for large diverts when the vehicle has to go through large tilts and attitude maneuvers. So we want to get to the point where we can do 6 degrees of freedom on this sort of scale of seconds for generating trajectory. Now, looking at visualizing the result of the transformer, so trying to understand what the transformer was learning, we saw that T-Sneal suggested that the transformer-based guidance efficiently characterized the samples based on which ones were tight constraints and the final time predictions. And we saw that there was two groupings. One grouping had a lot of tight constraints. One grouping didn't have so many tight constraints. And the transformer was really separating the problem into kind of these two groupings. One lobe of the T-Sneal plot corresponded to the tight constraint range around the sample trajectory, indicating that you can get more efficient solutions, and the transformer was more confident for this input range. And the transformer-based approach is generalizable to any optimization problem. So what we're showing you here, you can try it on other problems, but we just tried it on this one. So the results here are for the entry, descent, landing problem. And so we're looking at other approaches. This utilized the mean square error training, and then the accuracy predictions are prioritized over constraint satisfaction. But we're looking at other approaches for future work on other cost functions. We do have a paper if anyone's interested on looking at other cost functions for this problem here, and I'll just put it in the question slide. So if you're interested in this problem, but maybe investigating other cost functions, we have a constraint-informed learning full paper on that. The GitHub for our implementation of the transformer-based tight constraint predictions. If you want to try it on your problem, trajectory optimization, you can find that there. And our full paper is here. Do want to acknowledge support from NASA here. We had collaborators at JPL that also supported this work. And with that, hopefully we have some time for questions.
Ample time for questions. Sure. All right.
Hi, can you hear me?
Yeah.
Thank you for the presentation. So obviously the computation time was drastically decreased with respect to the other methods for this trajectory optimization. My question is, do you have any numbers on the loss of optimality from this process? Because the conical problem seemed like you get an optimal solution, and then with this prediction-based constraints, what kind of numbers do you see with loss of optimality there?
That's a good question. Let me see if I can get back to this slide. Actually, I think it's on. Yeah. So the base problem didn't change. So when what the transformer was doing was determining which one of these. Think about the transformer going through and crossing out these equations, just putting a line through it and saying, you don't need that one, you don't need that one, you don't need this one. But the base problem didn't change. But internally to the base problem, that knowledge of which constraints are active can significantly reduce the optimization space that you need. for solving the problem. So the base problem didn't change. It's still this base problem. At most, we're running the same speed as this. So at most, we're running the same speed of what I coded you earlier. Hopefully, we're doing better. But the worst we can do is with this problem.
So there is no loss of optimality?
There shouldn't be. The only thing that you were concerned about is feasible solutions. Like if you could generate a loss of run slower if you output, if you somehow the constraint tightness is wrong, and the optimizer can't find a feasible solution for what you told it, but then you can iterate and solve the original problem again in that case. So that's why we have that loop. If it fails, go back and solve the original problem.
Cool, thank you. And I just had a quick follow-up.
Sure.
Where does this extend for when you have like stochastic state estimation? Like it seems like there's no reasoning here about like maybe with ground-based navigation, there's a lot of uncertainty. Is that baked into this problem or?
Not yet, but the way that's, I mean, it could be applied in space is like an MPC kind of structure, but not yet. So one way we could do this is run this online, an MPC structure, and there is uncertainty in space. So like, for example, when you look at some of the neural network solutions we were doing for the EDL problem, one of the reasons we were interested in this is because when you're going through an atmosphere, the uncertainty of where you're going to turn on your engines can be quite large. So where you actually turn on your engines, so you're going aerodynamically to this point, then you turn on your engines. So that can be quite large, that uncertainty.
Cool, thank you.
Thank you for the talk. I'm wondering if you talk about, I know that this improves like the average time, but what about like the worst case time? Because presumably you have to run the transformer and then you might have to run your optimization problem multiple times if you have an infeasible solution.
Yeah, I don't have it. I might have it in the backup slide, so I'm not going to quote it off my head. But even the worst case time, like we have tables in the paper. We have all the statistics in the paper. So the worst case time was still better than what we got for. Obviously, the worst case is all constraints are active. So what's the all constraints are active? And like actually that goes back to your, it should always be better, but the worst case is, one second here. Yeah, so the worst case is all of these are active, right? That's the worst case scenario. An even worse case is actually these two are active, but you just told me all of them were active. That's the worst that, or one was active or none were active, but the transformer outputted that all of them were active. Then the optimization approach has to, account for all of those constraints, and all those additional equations that I mentioned earlier are included, but in reality, you gave me the wrong estimate. That shouldn't do any worse than the original problem.
Right, that makes sense. I guess how long does the transformer take to inference? Is that included in this time?
It is included in the inference time, but I think the transformer time compared to this is a relatively small transformer, is negligible compared to the runtime.
Okay, thank you.
But it's all in the paper. I just don't have it in the slides. All of the details are in the paper. Thank you for that question.
Other questions? Yeah.
I had a question about hardware. So what are how does this push the compute on a spacecraft that people would currently want to deploy? Does this solution push it? Do you need, and what are your challenges in terms of getting more compute on space hardware?
Yeah, so this is kind of more aligned with what exists for space hardware. So it's not like pushing the envelope in terms of demanding more compute. But in space, a lot of it is radiation hardening if you're going to another planet. Right. And like that typically lags behind. But like even like GPUs are rarely used in space applications. So like new computing architectures are rarely used, and a lot of it has to do with flight heritage. So if something has flown, people are more confident with it, they're more comfortable. Because we're doing one-off multi-million-dollar potentially billion-dollar missions.
So do you have challenges even selling this algorithm, for example, to JPL to deploy it, or?
No, I mean, maybe we're in a little bit of a bubble. The people that we work with are super excited about it. We're working with Johnson, which is the lead EDL folks at NASA. They're very excited about it. They like it. When you talk general like AI, they're skeptical, of course. Like I think that's always the case for space people. But I think they're ready to accept new approaches. It's been like that for years, that they're skeptical of AI.
Another question I had was, have you tried UMAP instead of TSNE?
So UMAP, so that's like UNet, a UNet or?
It's another, it's basically, I think it's a faster version.
Oh, instead of TSNE, okay,
it's like
yeah.
a faster version
All
of
right.
TSNE, I think.
Yeah. No,
And
we haven't.
I remember trying it at a last job. Now I can't remember. I was thinking you would, remind me why we actually were using it. Now I can't remember.
Yeah. No, that's a TSNE, my student
I
selected
think that TSNE allows you to actually have a model of the data, whereas TSNE is more of an interpretation tool. It's something to look at when you
We'll look at it, yeah.
Yeah. Thanks.
I'll have to write that down. Thank you for the suggestion.
Other questions? So I was curious how, in your, collaboration with your counterparts at Johnson, have you already started discussing how you go about the validation of these algorithms, how to make sure that the statistical analysis that you have, for example, in terms of worst case analysis and so forth, meets, the threshold to really have a manager approve these algorithms?
That's a good question.
Or is something that you're still, in terms of maybe how you can generate particularly problematic scenarios and so on and so forth?
Yeah, that's a good question. I think some of the techniques that I mentioned earlier on, like just full model-free RL, is way away from them like going through that process. But I think the really nice part about this is even the second-order cone problem, they're not there yet on that. So they're probably a couple of generations, but they're working with Bichek, which is one of the authors of that. So they're getting there on that. So I think they're probably open to this, but they're a few generations behind even some of the techniques that we're building on.
Right.
But I think that they are open to it. They supported this work, and
Yeah, that's great.
yeah. But they're still a few generations behind. They're very aggressive. They want to add this into their pipeline.
Other questions? Yeah.
You mentioned you used the one-hot encoding for your constraint satisfaction problem. Did you consider, can you walk me through what would happen if you used a weighted mechanism instead, where you were basically weighting each of the constraints as to their relevance at any given node or point in time?
That's a good suggestion. I'll take that back to my student. So I think that's a really good comment. Yeah, I'm trying to think of how we could implement that. One thing you could maybe do is certain constraints might be more expensive, whether they're on and off, and you should value, you need to really, if you need to be sure about telling me this constraint is valid. We haven't done that, but that's I like that. That's a good question.
Yeah, when you say some part of the constraints are inactive, is it inactive throughout the entire trajectory, or can you also? Well, I'm just trying to think about actually, can you elaborate? When you say some part of the inequality constraints are inactive, what does it actually mean?
Well, so remember, let me see if I can get the animation to play here. Oh, that's the problem of having fancy slides. My computer's a little bit frozen. All right, so you see this here? When you convert the problem to discretized problem, then you have these n constraints. So when a constraint is active, is for that node is active. So you have a glide slope constraint. Let's say it gets on the glide slope, but it might only be on the glide slope for 3 nodes. So by being active, you have 3 of these equations that are predicted to be active. So the constraints might not be active for the majority, but there's a lot of equations. And you just kind of want to know, where is it really active? Is it active at the end, Why do I need glide slope at the beginning? Things like that.
Thank you.
So like maybe another, I really like that question, but another video that I have in the slides that could highlight, sorry about that, is this. This I think explains that point. So this video here, you see that at this point, the red curve dips under the glide slope constraint. So it's only active for that point. So if I divided that trajectory into the control points for the direct solver, it would only predict, don't worry about the constraint, but just worry about it here.
Any more questions?
So along the same vein of if a constraint is active, is there any probability or any occurrences of the transformer thinking that a constraint is not active when it actually is active? And is there any way to, say, catch that? Or are you just kind of iterating back over the path?
Yeah, the way to catch it is that you would predict that it's not feasible because it's not in the feasible space. But in some of the test cases, I got to go to the slide, but in some of the test cases, sorry, I went too far here. So in some of the test cases that we ran, we got 100% feasibility. But if you predicted it wrong, like for example, like the initial condition is already violating the constraint, and somehow the transformer said that constraint is not active, then you'd get a feasible, infeasible solution. Yeah.
All right, so if there are no additional questions, let's give a round of applause.